Hey guys, in this short video, we're going to be taking a look at some examples of how to use conservation of momentum. So we're going to start with the condition that gives us conservation of momentum, namely that as long as there are no external forces, then the total initial momentum is equal to the total final momentum. So that is our condition right here, and this is only satisfied if the net force is 0. This is the net force on the system. The reason that we say this is that, as we saw in our demo, a net force times a time interval causes a change in momentum. So if F net is 0, that means that the change in momentum is 0, and that gives us this equation here. So what we're going to do is we're going to specify the impulsive force event from external to the system that separates the initial and final situations. We're going to designate objects in the system by listing the object, its mass, and its velocity in a chart, and we're going to use variables for unknown quantities. We're going to draw a horizontal bar to represent the size and direction of the momentum for each object. Because momentum is a vector, we have to take into account direction, and we are going to write the conservation of momentum equation, which is this, for the bars and solve for the unknown quantity. So this is going to be very similar to the LOL charts or the energy bar charts that we did last unit. Here's our first example. A 40-kilogram girl rollerblades at 4 meters per second towards her dog of 20 kilograms who is running at 7 meters per second in the opposite direction. The dog leaps into her arms and they roll off together. What is their final velocity together? So first of all, the impulsive force event is the dog jumping into the arms. And it's good to just sort of draw a diagram of what's happening. So you have the rollerblader going this way, and you have the dog, pretend, going this way. Okay, so we designate the objects in the system by listing the object, the mass, and velocity in the chart. So we have the girl who has a mass of 40 kilograms and an initial velocity of plus 4 meters per second. Now, we're going to say in our diagram that to the right is the positive direction. So that's good to specify. So 40 kilograms for the girl, moving at 4 meters per second. The dog is 20 kilograms, moving at, therefore, negative 7 meters per second. So we'll put that here. We have the dog, who's 20 kilograms, going at negative 7 meters per second. So now what we do is we calculate the momentum. And momentum is mass times velocity. We have to take into account direction. So 40 times 4 is 160. And so what we might want to do is make a mark here that this represents 160, and the units will be kilogram meters per second, and the girl has 160 units. It's just a bar chart, but sideways. The dog has 20 times negative 7, which is 140, and if we seem to be doing 40 per box, that's going to be right about here. So the dog has negative momentum of negative 140. And now, one thing that we can do is we can draw the total momentum of the entire system, and that comes out to be about 20. And that, of course, is 160 minus 140. Now, we do the same thing for the final situation. And what we have is we have the girl plus the dog, okay? So girl and dog. Since they're traveling together, they now have a combined mass of 60 kilograms. And their velocities are unknown, that we put in here as VF. Okay? And that's really all that we know. However, if momentum is conserved, then the total amount of momentum before the collision, which is our plus 20 right here, is going to be exactly the same as the total amount of momentum after the collision, which will still be plus 20. Now notice that during the collision, the dog and the girl are exerting forces on each other. But just like our CART lab, those forces are contained to the inside or internal to the system. Okay? So the girl pushes the dog backwards and the dog pushes the girl backwards. Okay? Technically the girl pushes the dog forwards, but for the dog he's slowing down. Okay. So now we apply conservation of momentum, and by the way, if we know that the total momentum is 20, the only object that we have in our system must have 20 units of momentum for that to work. Okay, so now we do conservation of momentum. Momentum initial equals momentum final. Momentum initial will be 40 kilograms times 4 meters per second. That's our 140, plus 20 kilograms times negative 7 meters per second. That's our negative 140. And that comes out to 20. That is going to be equal to the combined momentum of the girl plus dog, which is 60 kilograms times V final. So that's 60 VF, which means that V final is about 1/3 or 0.33 meters per second in the positive direction. Let's do another example. Two kids are at rest in office chairs and they push off. M1 is 20 kilograms, moving at 3.5 meters per second after the push. So we'll call this M1, which is 20 kilograms, which will move, we'll say M1 is going backwards, so that's negative 3.5. M2 is larger. M2 is 50 kilograms and moves at an unknown speed, V final 2. Whoops, sorry. What is the second kid's velocity after the push? So first of all, we specify the impulsive force event, that is the push off. We designate objects in the system. So we have M1, which has a mass of 20 kilograms, which has an initial velocity of 0. Notice that this diagram here is what happens after they push off. Before they push off, they just look like this. They're just sitting there, much like our CART explosion lab. Then we also have M2, which probably should be capital, should be switched, but it's okay. And this is also 0. So just like a bar chart for energy, we can specify something has 0 momentum by just putting a little X on that 0 line. That way you can tell that that's what we mean. This also means that the total starting momentum of the system must be 0. And that also means that according to conservation of momentum, the final momentum of the system must be 0. However, now this is like our carts where we have things going opposite directions. So we have M1 with 20 kilograms going at negative 3.5 meters per second. Okay, so that is 70 units of momentum. Let's make each box be worth 20. So that's negative 70 right there. And we just indicate it with that. Okay, then we have M2, it's lowercase, 50 kilograms, moving at an unknown speed, V final 2. We don't know that speed, but we do know that in order to get 0 total momentum, this had better be positive 70. Okay, so now we're set to do our conservation of momentum equation, and we can go from there. Momentum initial is equal to momentum final. So this is pretty simple. 20 kilograms for M1 times 0 plus 50 kilograms for M2 times 0 equals, that's 0 by the way, 20 kilograms times negative 3.5 meters per second plus 50 kilograms times v final 2. Notice that we're not making any assumptions about the direction of v final 2. We're just letting the math tell us what it is, and we're just using a plus sign here. So obviously this is going to be negative 70 kilogram meters per second plus 50 kilograms times v final 2. Solving this for v final 2, I'll just write it here because I was getting a bit short on space. That's going to be plus 1.4 meters per second. And excuse me. So that is in the positive direction as we thought, and that conserves momentum. Okay, so that's how we set up these problems. We draw a little diagram and pick a positive direction. So to the right was positive, in case you didn't figure that out. And we go through the process. We set up a bar chart for the initial event, okay, before the event. We set up a bar chart for afterwards, and that's pretty much it. So now, please use these examples to do worksheet 3.